All right, we're going to introduce a new idea here, something called the Laplace transform. And this is going to be a really important tool that we're going to use in order to solve differential equations. And it's not going to be clear yet, but basically we're going to take an integral, and because of the relationship between integrals and derivatives, it's going to be able to turn our differential equations into algebra problems. It's going to be really odd at first, and it's just something you need to practice and get used to and try and look at it in different ways. Before we do anything, I want to first note what happens when you take a definite integral. The meaning of this integral is if I go from 0 off to infinity, I'm finding the area underneath this function. So when I go to actually calculate this thing, I can turn it, it's an improper integral, so I have to be a little careful. So I can write it as a definite integral from 0 to m of e to the minus 3t, and then take the limit of that. Now I can use the fundamental theorem of calculus. This is going to be minus 1/3 e to the minus 3t from 0 to m. And I plug in my bounds. I get minus 1/3 e to the minus 3m minus a minus 1/3 e to the minus 3 times 0. As m gets really big, this thing goes to 0. It gets closer and closer to 0. And this just remains at 1/3. And so that integral is 1/3. What's important for us is that when you integrate that thing, you're removing the t. There's no t here. This is not a function of t. So when you do a definite integral, that definite integral basically removes that dummy variable, and it's that dummy variable doesn't really matter. Okay. So why is that going to be important? So notice if I change that, so I'm looking at the same thing, only instead of using e to the minus 3t, I'm going to use some number s. I'm going to ask what happens now. Well, again, I got to turn it into a limit of a proper integral. And I need to do this so that I can use the fundamental theorem. So this becomes the limit as m gets big. Now I treat the s as a constant. So this is just like what you did in Calc 3. So my integral looks like it's e to the minus 1 over s times e to the minus st. The bounds go from 0 to m. So I can plug in the bounds. So I get minus 1 over s times e to the minus s over m minus a minus 1 over s. And now I plug in t equals 0, so I get e to the minus s times 0. I have to be a little careful. What happens here depends on s. If f is a positive number, then e to the minus s times m is going to get closer and closer to 0 as m gets bigger and bigger and bigger, so that whole term gets close to 0. So I'm left with 1 over s times e to the 0, which is 1. Again, what's important here, there's no mention of t. Right? This is now a function of this parameter s. Once I find the area under this function, the only thing matters is the parameter s. It's going to give you different numbers for different values of s, assuming s is positive. And this is not a function of time. So when you integrate, take a definite integral, you're removing that variable and you're adding stuff up over that whole variable. Based on this is going to give us a definition. And this definition is going to be something called the Laplace transform. And the idea is we're going to take a function f of t, and the notation is, we're going to call it script L of f. This is going to be a function of s because there's going to be a parameter in here. But what we do is we're going to take an integral from 0 to infinity of our function times e to the minus st dt. Now I got to be a little careful. This doesn't necessarily exist for every f of t. So if it exists, then it's going to be this thing here. And notice I'm integrating over t. So in the end, there should be no t's left over, only an s. So this is a function of s. Okay. Again, it's a little difficult now to see why we're doing this. It won't be clear until we see some things later. But for now, it's important to note is if you happen to have the Laplace transform of f, there's only one function that gives you that result. So if you know the Laplace transform of something, you can figure out the original function. And very roughly, integrals undo derivatives because of the fundamental theorem of calculus. So those two things are going to make these very useful when we work with differential equations. And what we're going to end up doing is we're just going to take a differential equation, multiply by that e to the minus st and integrate, and nice things will happen. So notice if I take the Laplace transform of 1, I just plug in f of t equals 1. This becomes, if I take the limit as m goes to infinity, antiderivative of e to the minus st is minus 1 over s e to the minus st from 0 to m. And this becomes minus 1 over s e to the minus sm minus a minus 1 over s e to the 0. And if f is positive, this thing will go to 0, and I'm just left with this. So I'm left with 1 over s. If I give you a function, you are expected to be able to find its Laplace transform from the definition, and you're expected to be able to go through and do it step by step. So for example, if I ask for the Laplace transform of t, you plug in the definition. It's the integral from 0 to infinity of the function times e to the minus st dt. And you should recognize we have to use integration by parts, and that the derivative of t is nicer than the derivative of these other things. So let's make our first guess will be u is equal to t. Once you make that decision, everything else is set. My dv is whatever's left, and that's going to define my v, which is going to be minus 1 over s e to the minus st. It's the antiderivative of this, and my derivative of t is 1, which gives me this. So now this becomes u times v, so I get minus 1 over st e to the minus st from 0 to infinity, minus the integral from 0 to infinity of v du, so I get a minus 1 over s e to the minus st dt. Okay, I'm not going to go through all these details, but you would be expected to explain why that goes to 0. Right, and the reason is, you can write that as t over e to the st, and you can use L'Hopital's rule to show that goes to 0. So then you're going to be left with, and now this 1 over s has nothing to do with t, so I can pull that out. So this becomes e to the minus st dt. And notice I already did this up here. So this is just 1 over s times the Laplace transform of 1, which was 1 over s. So I get 1 over s times 1 over s is 1 over s squared. That was fun. I know what you're thinking. You're thinking, what do you suppose the Laplace transform of t squared is? Well, from the definition, I can just plug t squared in, multiply by e to the minus st dt, and take the integral from 0 to infinity, and this is t goes from 0 to infinity. I can write this as t times t. Oops, let's do this. Let's stay with the t squared, because I need to do an antiderivative. Let's not make this too complicated. And so now I'm going to take a derivative of that, so that defines my u. Once I make that decision, my dv is decided. And once I have that, that defines my v, which is going to be minus 1 over s, e to the minus st. My du is going to be 2t. So this is going to be u times v. I got to put in my bounds from 0 to infinity, minus the integral over the same bounds, over the same variable, v du, so minus a minus. I'm going to have 1 over s times 2t times e to the minus st. Again, just for brevity's sake, I'm not going to show this, but you should be able to make the argument, oops, it's plus, why t squared over e to the st goes to 0 over these bounds. And again, you're going to use L'Hopital's rule. And what do you get? You're going to get, I can pull out the 1 over s, I can pull out the 2. This becomes the integral of t e to the minus st dt. And we've already done that. This is just the Laplace transform of t, which we decided was 1 over s squared. So the Laplace transform of t squared is 2 over s cubed. Okay. So what we have the Laplace transform of 1 is 1 over s. Laplace transform of t is 1 over s squared. Laplace transform of t squared is 2 over s cubed. If you go through and do this, again, you should be able to show that the Laplace transform of t cubed is going to be 3 times 2 over s to the 4th. Laplace transform of t to the 4th is 4 times 3 times 2 over s to the 5th on down. And in general, you can show that this is going to be true, because if you take the Laplace transform of t to the n from the definition, it's going to be t to the n times e to the minus st dt. Use integration by parts. Just like before, I'm going to take the derivative of t to the n because that's nicer. That immediately defines my dv, which defines v. Yep. And then my du is going to be defined. So this becomes uv. So I'll get minus 1 over s, t to the n, e to the minus st from 0 to infinity, minus the integral from 0 to infinity of v du, so minus a minus because of that. I can pull out the 1 over s and get n t to the n minus 1 e to the minus st from v du. This is going to go to 0, and you should be able to show this. And the n I can pull out because that's a constant. And then this is the Laplace transform of t to the n minus 1. And in the pattern we've already seen, this is going to look like n minus 1 times n minus 2 times n minus 3 down to 1 over s to the n minus 1 plus 1. And then when I multiplied the n over s, I get n times n minus 1 times n minus 2 all the way down to 1. And then the s to the n times s becomes s to the n plus 1. Let's see. These kind of things are going to come up a lot. And I don't want to write all this out every time. So we have shorthand notation. We're going to call that n factorial. So if n is an integer, n factorial, and we denote it as n exclamation point, is n times n minus 1 times n minus 2. And we keep doing that until we get down to 1. So 5 factorial is going to be 5 times 4 times 3 times 2 times 1. You are going to be tempted to simplify that. Do not simplify it. That's a perfectly legitimate way to write a number. Leave it like that. And trust me, it will make your life easier because it'll make it much easier to see patterns when they arise. Okay. So what do we have then? For example, if I have some f of t is 3 plus 5t minus 8t squared, the Laplace transform of f is going to be the Laplace transform of 3 plus 5t minus 8t squared. Notice this is the integral from 0 to infinity of this function times e to the minus st dt. I can multiply that e to the minus st through for each term. I can break this. I'm going to assume I can do all these integrals. If each of these integrals exists, then I can break them up into pieces. Yeah, let me leave it as minus 8t squared e to the minus st dt. And I can pull out these constants. So notice this is just all algebra. I can pull out the 8. And notice now I've done all these things. This is just the Laplace transform of 1, 3 times the Laplace transform of 1, plus 5 times the Laplace transform of t, minus 8 times the Laplace transform of t squared. And if you know these patterns and know what these things are, this just becomes 3 over s plus 5 over s squared minus 8 times 2 factorial over x cubed. And there's my Laplace transform. And because I know that the Laplace transform of t to the n is n factorial over s to the n plus 1, dealing with things in this form becomes easy. Okay. We also have, if I look at the Laplace transform of f of t plus g of t, if the Laplace transform of f and the Laplace transform of g exist, then this just becomes the Laplace transform of f plus the Laplace transform of g. All right. Also, and if I take the Laplace transform of a constant times f, I can just pull that constant out. It just becomes a times the Laplace transform of f. This thing is an integral. You know, you can think of it as an integral, and it obeys all the same properties of integrals. So, for example, if I say that f of t is 4 over s minus 3 over s squared, oops, Sorry, let me rewrite this as 4 minus 3t plus 7t squared. The Laplace transform of f is going to be 4 times the Laplace transform of 1 minus 3 times the Laplace transform of t plus 7 times the Laplace transform of t squared. So we get 4 over s minus 3 over s squared plus 7 times 2 factorial over s cubed. By the way, notice if I start with this, and I want to know how do I go backwards? So if I know that the Laplace transform of f is 4 over s minus 3 over s squared, so it's 2 factorial is just 2 times 1 is 2. So this is 14 over s cubed. Suppose we know that. I can write this as 4 times 1 over s minus 3 times 1 over s squared. And now I have an s cubed here. I know that if I have a 2 factorial there, this is going to be the Laplace transform of t squared. But I can't just multiply by 2 factorial. If I multiply by 2 factorial, I have to divide by 2 factorial. So this whole term here is equivalent to that. I wanted a 2 factorial there, so I multiplied and divided. And now, this is the 4 times Laplace transform of 1 minus 3 times Laplace transform of t plus 14 over 2 factorial times the Laplace transform of t squared. And I can think of this as 4 minus the Laplace transform of 4 minus 3t plus 14 over 2 factorial t squared. So if you're given this, you should be able to figure out that the original function is 4 minus 3t plus 14 over 2 factorial t squared. And again, that's a perfectly legitimate way to write a number. All right, another example. Laplace transform. Oops, let me do this. So f of t is 5t cubed minus 17t to the fifth. Laplace transform of f is going to be 5 times the Laplace transform of t cubed minus 17 times the Laplace transform of t to the fifth. So here n is 3, so this is going to be s to the fourth, and the numerator is going to be 3 factorial. And here I'm going to have 5 factorial over s to the sixth. Okay, and it's perfectly fine to leave this in this form. But also recognize that you are expected to be able to go backwards, and if I give you this, you should be able to work it and recognize that that thing came from that function. Okay, so what do we have at this point? We have the Laplace transform of a function is defined to be the integral of the function times e to the minus st dt from 0 to infinity, with the caveat that it may not exist. If it exists, then that's what we're going to use. And we have the Laplace transform of f plus g is equal to the Laplace transform of f plus Laplace transform of g. Laplace transform of a constant times f is equal to a times the Laplace transform of f. And the Laplace transform of t to the n is n factorial over s to the n plus 1, and we're assuming n is an integer.